Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heat transfer analysis, parametric study and optimization of a cross-flow heat exchanger using SolidWorks 2022. This is the actual model used in the specific process industry. To understand the geometry, let us have a segmented view of this model. We can cut it from different planes. First of all, we'll cut it from front plane and let us drag it a little bit inside. You can see these are the tubes. Through these tubes, cold water will be passing, and from sideways we will provide hot air at a temperature of 250 degrees centigrade. And this is the inlet of cold water, this is the exit. Similarly, this side is the inlet of hot air, and on the other side, this side is the exit of hot air, right? Let us rotate this one and see. This side is the exit of hot air. To understand the geometry of this pipe, we can have it another sectional view. We can cut it from right plane. These are the tubes, which is made up of copper. These are not normal tube. To have more surface area, we have provided some kind of extra element inside these pipes or tubes, and this extra element is in the form of some spiral. You can see it here. See, these are not actually hollow tubes. Inside these tubes we have provided some kind of extra elements to provide more surface area, and the elements are provided in the form of spiral. This model is actually used in a specific industry, right? So geometry is clearly understood. Now for initiating flow solution, we have to start from here, and for initiation of flow solution environment, we need to start from wizard. And we're keeping the name of the project as project 2 because project 1 we have already performed. Next to that, we need to select unit system as SI, and we'll consider temperature as degrees Celsius. Next to that, it will be an internal analysis, and from physical features we'll select fluid flow with conduction, and gravity will be involved. Direction of gravity will be Y as indicated by this arrow in the upward direction. So along Y it will be minus 9.81 meter per second square, and along Z it will be 0. Done. Next to that, we need to select fluids. In this case we are considering two different fluids, water and air. So let's select water from here, and the second fluid will be air. We will consider two different fluids, water and air. Next to that, we need to select materials. We are considering the inner part is made up of copper, that is tubes are made up of copper, and the shell is made up of stainless steel 321. So from here we can select metals, and it will be copper, and the other element will be selected during application of boundary conditions. Next to that, we need to select default outer wall thermal conditions and roughness, and finally we'll select thermodynamic parameters as pressure should be 101.325 Pascal and temperature should be 20 degrees centigrade. Again, solid parameters also it will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. We can hide it and provide different fluid subdomains. And for providing fluid subdomains, we can have a segmented view of this model. So we can cut it from top plane and drag it upward. This is better one. Okay, right. For providing fluid subdomains, let us rotate this one. From this one, water at a temperature of 20 degrees centigrade will be passing, and that will flow through these copper tubes, right? So fluid subdomains, insert fluid subdomain, and it will be water at a temperature of 20 degrees centigrade. You can see thermodynamic parameters, pressure is 101.325 Pascal and temperature is 20 degrees centigrade. That will be passing from this opening. Grain check. You can see this is the fluid subdomain for cooled water. Let us hide it. Next to that, you want to see fluid subdomain for hot air. So again, insert fluid subdomain. It will be air, and that will be passing from this side at a temperature of 250 degrees centigrade. Let us increase the temperature from here. It will be 250 degrees centigrade air. Let us rotate this one a little bit. We can select that specific location from where hot air will be passing. This one. From sidewise, we will provide hot air. So this is the fluid subdomain for hot air. Right? Grain check. There will not be any mixing of hot air and cold fluid. By convection only, cold air will be heated up. So fluid subdomains are defined. Next to that, we need to provide our materials. Insert solid materials, predefined metals, and from metals we have to select copper, and we can select the material from the solid geometry itself. All the tubes are selected and it is made of copper. Grain check. Next to that, we need to select the shell, that is the outer surface, which is the outer body or the casing, which is made up of stainless steel 321. So solid materials, insert solid materials, and it will be made up of stainless steel 321. Predefined alloys, it will be stainless steel 321, and you can select the materials from here. It will be, we have already named this one as top face and casings. Let us select all these things. The casing and the defined faces together with the leads are made up of stainless steel 321. Grain check. So both the materials are defined. Next to that, we need to apply our boundary conditions, right? Boundary conditions. Insert boundary condition. We need to provide air from this side at a velocity of 0.1 meter per second. Let us rotate this one a little bit. It will be inlet velocity, and we are providing air at a velocity of 0.1 meter per second from this side. And let us see thermodynamic parameters. It will be 250 degrees centigrade, right? Grain check. Another boundary condition is needed. That means we need to provide water from here at a temperature of 20 degrees centigrade and at a velocity of 0.1 meter per second. We can rename this one also again as inlet velocity of hot air. Second one, insert boundary condition, and it will be inlet velocity, and it will be coming out from this location, and velocity it will be 0.1 meter per second, and thermodynamic parameters it will be 20 degrees centigrade. Grain check. It's done. Two more boundary conditions are needed. That means it will be atmospheric pressure at the exit locations. Let us rotate the model a little bit. We can rename this one as inlet velocity of cold water. Two more boundary conditions are needed. Insert boundary condition. It will be atmospheric pressure at the exit locations. We can select this one. This is the exit of hot air. Green check. Another boundary condition is needed at the exit of cold water. Insert boundary condition, and again it will be atmospheric pressure at the exit of cold water. Green check. Done. And we rename this one as environmental pressure at hot air exit, and the second one will be environmental pressure at the cold water exit. Done. Next to that, we need to find some goals. So goals, insert surface goals. We need to find average temperature of fluid at the exit of hot water and cold water. Let us select the surfaces separately. This is the exit surface of hot air, that is indicated by phase 1, and this one is the exit of cold water, indicated by phase 2, and we will create these goals separately. Green check. Both the surface goals are defined. We can rename this one again. First one is average temperature of hot air at exit, and the second one is average temperature of cold water at exit. So all the goals are defined. Now we can run it. We have already done this one in project 1. Now we can view these results from project 1, right? Let us load the results. For viewing the different cut plots of pressure, temperature, and also the dynamics of flow particles, let us make the model completely transparent. You can see the model is completely transparent. Now you can see different cut plots of pressure, temperature, and also dynamics of flow particles through this heat exchanger. Right, we can see it. You can see very clearly that through these pipes we have provided some kind of extra element in the form of spiral, and that will be providing more surface area. First of all, it will be cut plots of temperature distribution from different planes, right? So cut plots, insert cut plots, and you will see temperature distribution. It will be temperature of fluid, and you will see that one from the right plane. Green check. So you can see inside these pipes temperature is different. It is having mixed zone. Let us see this cut plots in the form of an animation. You can see from left hand side hot air at a temperature of 250 degrees centigrade is passing. By the same time, from back side through these pipes or through these tubes, water at a temperature of 20 degrees centigrade is passing. Let us rotate this one a little bit to understand this view. From the back side, you are providing cold water at a temperature of 20 degrees centigrade, and from sideways we are providing hot air at a temperature of 250 degrees centigrade. And we're going to see this distribution from other plane. Let us clear and hide this one, and we're going to see this cut plots of pressure and temperature from other plane. Cut plot 1, edit definition, and we're going to see it from different plane. Let us see it from front plane. Green check. It will be better to see this from front plane. We can change the orientation of this model. Now we can view it in the form of an animation. Let us play. We can rotate this one a little bit to understand this one in a different way, right? So what we are doing is, from this side we are providing hot air at a temperature 250 degrees centigrade. The color is red, that means temperature at this location is very high, and as it is approaching to the other sides, its temperature is little bit reduced. At the same time, from back side we are providing water at a temperature of 20 degrees centigrade that is passing through the tubes, right? Let us clear and hide this one. Next to that, I want to see surface plots. We're going to see temperature distribution through the surface of this heat exchanger. insert surface plots, and when you see temperature of fluid, and we'll be using all phases. Green check. You can see at different phases temperature is different. This is the inlet location of hot air, so its temperature is 250 degrees centigrade, and this is the exit location of cold water, and its temperature is in mix zone. And you can see there is a mix zone at the exit of cold water. We're having different color ranges at the exit of cold water, and you can see the back side of this one. You can see that much of change in temperature is not visible. Only at the bottom side we're having some decrease in temperature of hot air, and this is the inlet of cold water, and its temperature is in the blue zone. That means it is in the range of 20 degrees centigrade. And inside this one we have provided some kind of baffles. This is the baffle, right? Let us clear and hide this one. Next to that, you want to see dynamics of flow particles. That means how the different fluid particles will be moving through this heat exchanger. So flow trajectories, insert, and instead of 20 numbers we want to make this one 200 numbers of flow particles, and the size of particles we're considering as 0.03 meter, as this is actually a very big model. This model is used in a specific processing industry. Let us start from the locations from which the particles will be starting. And for seeing the dynamics of flow particles, let us have a segmented view of this model. We can cut it from top plane and we can drag it a little bit upside. So flow trajectories, insert, and instead of 20 numbers of flow particles we are making this one as 200 numbers of flow particles will be moving through this heat exchanger. Let us select the cold region, that means from which water will be entering. This is the entry location of cold water, and we need to select hot air location also. Hot air will be starting from this location. For that we need to rotate this one a little bit. This is the inlet location of hot air. We need to select some other locations also. This is the exit of cold water, and this is the exit of hot air. So through these surfaces we'll see dynamics of flow particles, right? Green check. Particle study is running right now. It will take some time for generating all these flow particles. You can see this one in the form of an animation. Let us play. You can view it from different planes. From here we are providing cold water at a temperature of 20 degrees centigrade. It will be passing in the forward direction. By the same time, from sidewise we are providing hot air at a temperature of 250 degrees centigrade. In this case there is no direct mixing of hot fluid and cold fluid. By convection only this cold water will be heated up. Okay, let us clear and hide this one. Next to that we want to see our goal plots. This is our complete model. Now we want to see our goal plots. From here, insert goal plots, and we want to see all the goals. Let us export it to Excel. Let us see the average temperature of water at exit. You can see after 101 numbers of iterations, the average temperature of water at exit is 86.04 degrees centigrade. So we can see that there is huge amount of rise in temperature of cold water. Initially temperature of cold water was 20 degrees centigrade, and here after 101 numbers of iterations we can see the temperature at the exit of cold water is 86.04 degrees centigrade. Next one is average temperature of air at the exit location. Initially average temperature of air was 250 degrees centigrade. Here you can see after 101 numbers of iterations the temperature at the exit of hot air is 240.7 degrees centigrade. We cannot see that much of decrease in temperature of hot air, only 10 degrees centigrade decrease in temperature. But by the same time you can see there is huge amount of gain in temperature of cold water, right? Let us close it. Next to that we want to go for some kind of parametric study with a design of experiments and optimization. We have already done this one. Let us see it. Inlet velocity of hot air we have varied. from the range of 0.01 meter per second to 1 meter per second. And by varying the inlet velocity of hot air, we can have different values for cold water. Let us see the scenario. We have undergone 6 set of experiments, and you can see when the inlet velocity of hot air is 0.01 meter per second, in that case the average temperature of hot air at exit is 240.86 degrees centigrade, and that of cold water is 79.46 degrees centigrade. In experiment number 2, when the inlet velocity of hot air is 0.05 meter per second, in that case you can see temperature at the exit of hot air is 240.71 degrees centigrade, and that of cold water is 83.68 degrees centigrade. In experiment number 3, when inlet velocity of hot air is 0.15 meter per second, in that case temperature at the exit of hot air is 230.25 degrees centigrade, and that of cold water is 83.03 degrees centigrade. In experiment number 4, when the inlet velocity of hot air is 0.25 meter per second, in that case temperature at the exit of hot air is 230.15 degrees centigrade, and that of cold water is 85.42 degrees centigrade. In experiment number 5, when the inlet velocity of hot air is 0.5 meter per second, in that case you can see temperature of hot air is very high. It is in the range of 237.44 degrees centigrade, and that of cold water is 89.71 degrees centigrade. It is also very high. And finally, in experiment number 6, when the inlet velocity of hot air is very high, it is in the range of 0.802 meter per second. In that case, the average temperature of hot air at exit is 240.43 degrees centigrade, and that of cold water is 90.436 degrees centigrade. It is very high, right? So it is clearly evident that if we are increasing the inlet velocity of hot air, in that case the temperature of cold water is increasing at the exit location. Initially, when the inlet velocity was very less, it is 0.01, it is 79.46 degrees centigrade for cold water, and when we are increasing the inlet velocity very high as 0.8 meter per second, in that case temperature at the exit of cold water is 90.436 degrees centigrade, right? Now instead of stopping it here, we can go for some kind of optimization. We have already done some kind of optimization. Let us see the optimization details. Actually, in this optimization, we wanted to have the temperature of cold water at the exit to be 90 degrees centigrade. For that, we need to select the inlet velocity of hot air in the range of 0.5 meter per second to 1 meter per second. Let us see the scenario. So after 5 design point, we got the results, right? You can see, to achieve the temperature of water at the exit location as 90 degrees centigrade, it has undergone 5 design experiments, and after 5 iterations, we could find that temperature at the exit of cold water is 90.02 degrees centigrade, and we targeted to achieve this value with a variation of 0.1 degrees centigrade. So discrepancy in this case is very less. Now you can see that when the inlet velocity of hot air is 0.5149445579 meter per second, in that case the temperature at the exit of cold water is 90.0239 degrees centigrade, and we could achieve this targeted value with a discrepancy of 0.023. It is very less, right? So we got our targeted value with a specific inlet velocity of hot air. With this one, we will conclude our today's analysis. This is a very simple analysis of a cross flow heat exchanger, and this type of heat exchangers are actually used in process industries. This is an actual model of the process industry, right? So thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.